So I'm trying to have a range of examples that might be relevant to or of interest to different people doing different, studying in different areas. So the next example I want to look at here is some relationship between seed production and flower spike length in grass trees. This data is from two sites, one in Mundaring, the other one is Yanchep. And so what you can see here is that I have measurements. I'm saying in here, if you look at the setup, on the vertical I've got seeds, and on the horizontal I've got the flower spike length. So I'm saying that the size of the flower spike length explains seed production. This is starting to get into some sort of observational space. I don't really have information on the age of these trees, so we might be thinking that there's good reasons for this different pattern that we see. So rather than use both locations, which is something that we can do, and so when you have a scatter plot, you often do try and display the groups differently, I'm just going to use the data from Mundaring to have a look at. And I'm really, in this example, I guess I want to show you that where things are not working so well, where we don't really see much of a strong relationship, but that the steps that we go through. So I just restrict my data set to the Mundaring data. We have a look at this and you can see that it just looks like a random scatter. Well, at least to me, it just looks like a random scatter. I'm a bit struggling intuitively to understand what to do with this, so I try a few different transformations. There's a log on the Y, well, it doesn't look much different. Log, and we've seen the linear, so there's my linear log. So none of them really seem to be giving me a convincing pattern of what's going on. So because of that, I would settle on the untransformed model because it's clearer. It has the most intuitive explanation. So I don't have any strong reason to select any of these four possible, data displays. They all look equally bad. So I select the one that is, the easiest to understand. So, well, okay, doesn't look like much is going on here. We still want to test this. So we still want to describe, is the slope statistically different from 0? Is there a positive slope? We would, biologically, we would be expecting a slope. And when we look at the combined data with the different locations, we see a bit more evidence of that. The other important thing to think about here is, it's something that I work on a lot, is making sure that we report null results. Okay, so if we find something that's not statistically significant, that is part of the literature. Okay, that's part of the investigation, and we still report those. It's not only about finding things that are statistically significant. All right, so we know that, we would expect to be making, remember there are type 1 and type 2 errors at play here. All right, so I don't have any strong reason to select a transformation. They all looked equally bad. I just go with the linear model. What do I find? Okay, so here's where this idea of these different levels of significance is coming into play. So I've run my model. You can see the model that I estimated up here had the form seeds explained by length, and it was I subset the data S1 seeds 1. It's just the Mundaring. There's my model. I saved it as lm.grass for grass trees. Now we're going to get our estimate of the slope here, and you can see that it's this guy divided by this guy gives us 1.7. Now remember I said for a 95% confidence interval, we know that it's around 2 is the critical value. But you can see here we get a p-value of 0.098. So while we would, applying our 0.05 standard, not reject the null, if someone wanted to apply the 0.1 standard, they would reject the null. Okay, so you could see that there's outcomes in this range where, depending on your view, the one that we traditionally take is the 95% confidence interval. But if you're prepared to work with the 90% confidence interval, and there's no reason why that's a problem, then you would reach a different conclusion. So that's why it's important for the way that we write up our results to give people, look, we'll give you the estimate, we give you the standard error, and we give you some specific information on the level of significance that you can conclude from that. How would we interpret the slope? Well, this is measured in meters, so it would be, and it's on the linear scale, so it would be a 1 unit. 1 unit is 1 meter increase in flower spike length leads to, on average, 1,045 more seeds. How do we write this up? So significant at the 1, not at the 1, at the 10. So 10 gets 1 star. So we have 1 star in here. We have the R squared value, which we saw back here. So low, so that's, consistent with our story. When we have a good fit to the data, this guy is high. When we have a poor fit to the data, this is low. So it says how much of the variation in the model are we explaining? We're explaining 14.4%. So we're not explaining a lot of the variation. We're explaining some, but not a lot. Others we're explaining like 97% of the variation in the data. Observations, and there's our description. So we have our table, important point for regression models, and the other important point is the figure. So the figure is the scatter plot with the trend line fitted. So this, you need this, and you need this. That is the essential thing for any regression model we're having. We're having a summary table, and we're having a summary figure of this form. And that's an opportune time for a break.